Hi guys, this is Math 116, section 2.3. We're still working with parabolas, and this whole section is business applications of quadratic equations and parabolas. So there's three main things that are covered in this section, and I have an example of each one. The first one is the break-even point. So in general, the break-even point is where the cost function equals the revenue function. And I think this makes sense intuitively if you think, well, you're breaking even when your costs equal your revenue. So your costs are the money that you are spending to pay employees and overhead and things like that. And your revenue is the money that's coming in. And when those two things equal each other, you're just breaking even, my friends. It's not the worst place to be. You're doing better than the U.S. government. But that's the break-even point. Here's an example of this. Question number 1 in the 10th edition, which happens to be number 15 on the 9th edition, reads, the total costs for a company are given by this cost function, C of x equals 2,000 plus 40x plus x squared, and the total revenue is given by this function, R of x equals 130x. X is the number of items of the commodity. Find the break-even points. Okay, we can do it. So the break-even points are, I need my pen. So here's question number 15. So we're going to set the cost function equal to the revenue function to find the break-even point. Revenue function. Breaking even. It's not bad. So the cost function was 2,000 plus 40x. This was all in the problem. Plus x squared, do you see how my x is starting to look like a plus there, equals 130x. That's sometimes why I make my x's a little wavy so they don't look like a plus sign. So now we're just going to solve, and we're going to make this equal to 0, and we want to find the x that makes these equal to each other. So we have x squared, we'll leave that on this side. We're going to subtract 130, so that's 130 on this side, minus 40, so that's negative 90x. Plus 2,000. I'm setting this all equal to 0. In order to solve the equation, you set everything equal to 0, and you find the x that makes this true. So to do this problem, we have our different methods. We could use the quadratic equation, right? What was that? We're not going to do that right now. X equals negative b, that one, plus or minus square root, or you can just factor, or you can use a graphing solution. In this case, I see the factoring right away. To me, I think, oh, 200. 200, you think that could be 20 and 10, right? But the difference of those is 10. We want 90. Haha! How about 50 and 40, right? 50 times 40 is 200. And when you subtract them, x minus 50, x minus 40, you get the negative 90 term equals 0. So this term, this whole thing is going to be equal to 0 when this term equals 0, or when x equals 50, or where this piece equals 0, or x equals 40. And again, the system we're using is you factor, and then if one of these factors equals 0, then that's a place where it equals 0. So here are the break-even points when x equals 50 and x equals 40. So the break-even, BE points, you could say BE points, I guess, is when x equals 50 items sold, or x equals 40 items sold. You could break even in both places. What's happening in the middle? Well, let's see. So here is, I mapped this out for you. Right here, x squared minus 90x plus 200. Here's the parabola. You can see that it opens upward because this coefficient in front of the x squared term is 1. So it opens up, and there the break-even points are where it crosses the x-axis. So that's at 40 and 50. So that's the graphing solution. If you're good with your graphing calculator, you can graph it and see where the parabola crosses the x-axis. But you still need to get the parabola equal to each other and get this parabola right here, this guy. Got to get that guy first. Okay, so that was the first type of problem. That's the break-even point problem. Here's the second type of problem, profit functions. So the profit is going to be your revenue minus your cost. And that, again, is a fairly intuitive business notion. The money that you have left over, your profit, is your revenue, all the money coming in, minus the cost that you're spending. So here's the formula. If your profit function is a downward facing parabola, then your maximum profit is going to be the vertex, the top point. and then the break-even points are where the parabola crosses the x-axis, and I have an example of that. So this example is question number 11, which is also 25 in the 9th edition. This section they really messed up they just really scattered the problem numbers. So this is question 11. The profit function for a certain commodity is P of x equals 110x minus x squared minus 1,000. X is our number of items. Find the level of production that yields maximum profit. So basically how many items should you make for maximum profit? So we're going to look at this parabola. Here's what we have. This is question number 11. We went up to 11. P of x is equal to 110x minus x squared minus 1,000. And we're saying what x is going to maximize this? Well, I'm going to rewrite it in the general form. This is just so you can get the a, b, and c. That's put the x squared term first. 100x squared plus 110x minus 100. Okay, so now we can see that this a term, we could have seen it over there, but it's negative. So that tells us that we have a parabola that opens down because of the negative coefficient of the x squared term. So it opens down. That means our vertex is going to be the maximum. So whatever this vertex is, it's the maximum because of the properties of quadratic equations. So now we're going to do what we did in the other section and say the vertex, home free. The vertex is x equals negative b divided by 2a. Nobody remembers that, but I do, and you're going to remember it too because I just told you. So now it's negative, we're plugging in, that's b right there, 110, divided by 2 times a, which is negative 1. A is the coefficient of the x squared term, and that equals 110 divided by 2 is 55. 55. So what is the maximum profit, or what is the maximum number of items that maximizes profit? X equals 55 items will maximize profit. Isn't that a handy application of that vertex? Maximizes profit. Sorry, my eyes are so strange with this touch tablet. Profit. Maximizes. So the other question said find the maximum profit. So what is the profit when we let x equal 55? We're plugging 55 in there, so it's 110 times 55 minus 55 squared minus 100, and that equals 2025. So the maximum profit is $2,025. I hope that's per week. Otherwise, that may not get you much of a business loan, guys. And then here is this graphed out. So here's that parabola, 110x minus x squared minus 1,000. This is the profit function now. And so this point right here, you can see again, it opens down. It's downward facing. So this point is the maximum, and that was what we said. 55 was the number of units, and 2025 is the profit. So this point is units, comma, profit. And then these points are the break-even points. So you're breaking even when you make 10 items, and then you're breaking even again at 100. So it seems like you kind of want to operate in this making 55 or less items. And so that was 2 of the 3 things that are covered in this section. So that was what I meant with profit functions. It's a downward-facing parabola. The break-even points are where it crosses the x-axis. The final thing in this section is market equilibrium. So if we have a supply and demand function, we might want to find P, the price, and Q, which is the number of items you're selling, that solves the 2 equations. So you want to find the market equilibrium price. To solve these, you're going to want to write one equation in terms of the other variable and then substitute and solve. This is essentially what we were doing in section 1.5. We're trying to solve a system of equations. So here's an example of these market equilibrium questions. This is question 27, which is number 6 in the 9th edition. If the demand function for a commodity is given by this function, p squared blah blah blah, and the supply function is given by the equation here, 300 minus p squared plus 2q equals 0. Find the equilibrium quantity. So how many should you make, and what is the price? So you want to find out given this supply and demand, what is the perfect quantity that you should be making and the price so that supply and demand perfectly equal each other. So this is how you do these problems. So this is question number, question 101, number 27. And here with the first equation we had was, here I'm going to write the two equations. We have p squared plus 4q equals 1600, and that was the demand function. And we also had 300 minus p squared plus 2q equals 0. This was your supply function. It's demand function. So now we want to find the p's, mind your p's and q's. Were you guys thinking that? We want to find a p and q that make both of these true. So that's going to be the market equilibrium. So the way you do this is you take one equation. It doesn't really matter, but again, this is very similar to section 1.5. I'll start with this one, and I'm going to write it in terms of q. So in this case, I'm going to say that's 4q is equal to, well, that'll be 1600 minus p squared. I'm doing this so I can substitute into this equation. And because this is a 2q right there, I'm just going to leave that one as 2q, divide all this by 2, and that'll be 800 minus 1/2 p squared, because my goal is to substitute here so that I have an equation that is all in terms of one variable. So now I'm going to write this one in terms of one variable. So I have 300 minus p squared. I'm going to leave it all in terms of p, plus, because this was plus. Now for this whole thing right there, 2q, I'm going to substitute this, 800 minus 1/2 p squared. Because it was plus, I didn't have any signs to mess around with. Now we get to solve for p. Yay, I just made an excited gesture with my hands and I realized you guys couldn't see it. So we have 800 and 300, that's 1100, minus, we got minus p squared and minus 1/2 p squared, that's minus 3/2 p squared. When I first did this, I thought, I may have made a mistake. This just doesn't seem right, but it is right. It's just not a very tidy number, but it doesn't mean it's wrong. Over here we have 1100 equals 3/2 p squared, la la la. So p, when you take the square root, is equal to 27.08. You'll notice it could be plus or minus 27.08 because you're taking a square root, you know, or here you're taking square root of that times 2 divided by 3, 27.08. But because we're looking at a price, p is price, and q is quantity, the number, so we don't want a negative price. That's giving it away, my friends. So our price is $27.08, and the quantity, well, what quantity do we get here? You can plug the price in here to get your quantity. So again, like 2q, you plug it right in here, equals 800 minus 1/2 times price, 27.08 squared, which is equal to 216.67. Your book says 216 and 2/3. That's fine also. Either one is fine. So you should be making about 216.67. I would have said 217, but that's fine. 216.67. I would also accept 217 items. I don't know, is that per week or per month? And you're charging $27.08 for them. And that is your equilibrium point. That's a perfect market equilibrium. Oh, in a perfect market, is there such a thing? So these are the three questions. Quickly, I'll go back over them again. Come on, Word. Here they are, the three types of questions we did in this section. We found the break-even point, so you're letting the cost equal the revenue. Profit functions, so you take the revenue minus the cost, and then you can maximize the profit by looking at the vertex, assuming it's a downward-facing parabola. And then finally, we had the market equilibrium problems, which is where you want to find the P and Q, the price and the quantity that makes the system of two equations work. So Those are the 3 types of problems in this section, and please let me know if you have any questions.